Hello, I am Sam Elliott. I am currently studying applied math at CU Boulder, and this summer I participated in NCAR's SciParks program, working on the implementation of a scalable, performance-portable, shallow water equation solver using radial basis function generated finite difference methods. In this video I will go through some slides and try to best sum up everything from my RMACC SRC poster. So first off, I would like to point out some extremely necessary abbreviations I will use throughout this video. First we have PDE for partial differential equation, RBFFD for radial basis function generated finite differences, SWE for shallow water equations, and RCM for reverse Cuthell-McGee. So the shallow water equations are a set of nonlinear hyperbolic PDEs that can be derived from depth integration of the Navier-Stokes equations. Therefore, they are an important stepping stone towards three-dimensional atmospheric dynamics simulation. On the right, I have a quick visualization of water waves to give you a bit of a sense of what the shallow water equations represent. With the inclusion of both the Coriolis and gravitational forces, the shallow water equations on a sphere can be represented as they are shown here. To numerically solve these equations, we used RBFFD methods, which are high-order, inherently meshless methods for solving PDEs. So for those who are unfamiliar with numerics, this essentially means we are able to very well approximate the spatial differentiation given in the PDE at each point with the weighted sum of the values at the points nearest to it. So our goal was to implement a scalable, performance-portable RBFFD shallow water equation solver. We wanted to target the three dominating architectures in current HPC systems, that being Intel multi-core, Intel many-core, and NVIDIA GPUs. By using OpenACC and OpenMP directives, we were able to express thread-level parallelism in a single source code that was portable and performed optimally on all three architectures. Although the unstructured nature of RBFs is elegant mathematically, the unstructured memory references and memory dependencies become very challenging from a parallel programmer's perspective. By using reverse Cuthell-McGee point ordering, which places points that are physically close to each other closer within memory, we were able to make these obstacles more tolerable. This allowed us to develop a relatively simple, efficient distributed memory model, which we then implemented in MPI. Here we are plotting the weak scaling performance in gigaflops of the solver on a single dual-socket Haswell CPU node, a single Intel Knights Landing node, and a single NVIDIA K40 GPU. So although there are some subtleties to the performance on each system, overall we see that the performance is quite satisfactory given the RBFFD method's complicated memory reference patterns. And actually, in optimal cases, we are even reaching over 15% of the theoretical peak performance. So optimizing and tuning MPI was the most challenging for GPU systems, whose interconnect is constrained by PCIe bandwidths and latencies. Because of this, we decided to present the strong scaling results of the MPI implementation for a Cirruscale GX8 dense GPU system, which is composed of 8 NVIDIA K40 GPUs on a PCIe interconnect. Here we are keeping the problem size constant, but increasing the number of GPUs used. The green bars represent the performance, and the blue line shows the MPI overhead. So from this we can see that the RBFFD solver is scaling very well. And when utilizing all 8 GPUs, the MPI overhead is around 6%, and we're actually achieving close to 1 teraflop. So to conclude, we implemented a single source hybrid MPI, OpenACC, OpenMP, RBFFD shallow water equation solver that 1. Demonstrated performance portability on the three dominant architectures used in modern HPC systems, and 2. Demonstrates high scalability, even on multi-GPU systems that are constrained by PCIe latencies. Foremost, I would like to thank my mentors Raj Kumar, Rich Loft, and Natasha Flyer for their continued support, as well as my SciParks co-interns and everyone else who made this project and my participation in it possible. I do greatly appreciate this opportunity and would especially like to thank RMACC for hosting this competition.